long-ish RNA molecule that folds up on itself. Big giant palindrome. Okay. It sort of provides the scaffolding for the remaining, for the protein. How many of you remember when we were in Bio 111, we did a fingerprint on you, we were looking for an ALU sequence? Whether you had an ALU sequence on, I think it was 16 or something like that, or not have an ALU sequence. The ALU sequence, you've got a little over 1 million copies of the gene, that, of a piece of DNA that codes for the ALU sequence. It's actually it evolved from this particular RNA gene. So if you think back to when you were a freshman and the ALU sequences, this is where ALU sequences came from. Okay, so there's a bunch of proteins. I'm just going to show you roughly what they are. This protein, which is sort of exposed by itself, is a GTPase. Okay, it's going to hydrolyze GTP. It's a quality control step. And as we go through this process, almost every time you see a GTP hydrolysis, it's sort of a quality control step. Okay, then there's a bunch of proteins here and here. Okay, these two are going to really interact with the ER membrane. RER stands for rough endoplasmic reticulum. What makes rough endoplasmic reticulum rough? Yeah, ribosomes are bound to them. Okay, you can do one other. And then, oh, I didn't leave enough space, so we'll put a couple smaller proteins on here. Okay, the last two proteins down here bind to the A7 on the ribosome. Okay, so this SRP is going to be binding to a lot of different things. Okay, the binding pocket here that is going to be the binding site for the signal sequence is a hydrophobic binding pocket. It's made up of a lot of really long hydrophobic R groups, and they work like brushes, and they can change shape, and so you can accommodate any kind of hydrophobic stretch of amino acids. So that's kind of a flexible binding pocket, preferably for hydrophobic amino acids. Hydrophilic amino acids would not would be rejected from the hydrophobic. Okay. So when a signal sequence emerges, and a signal sequence is something that has a large stretch of hydrophobic amino acids, okay, the signal recognition particle binds to the ribosome and blocks the A site. So what's going to happen to protein synthesis while the SRP is bound to the ribosome? It's going to stop. And why might that be important to stop the synthesis? This one not obvious until I tell you, and then we're going to go, oh, yeah. Tell me about the emerging stretch of amino acids. They're hydrophobic. If we allow protein synthesis to continue, where would they end up in the growing protein? Would they stay on the surface? No, they get buried. Okay, so if there's a temporary halt to protein synthesis, so that this this structure can form, and we're not going to continue to make the protein and then bury the signal sequence inside the growing protein. Okay, so that's kind of important. Okay, so ready for the ER. There's lots of SRPs floating around in the cytoplasm. In fact, a fairly large number of SRP molecules floating around in the cytoplasm. I should also give you a term for these kinds of complexes. Ribonucleoprotein, made up of RNA and protein. And the ribosome is a giant ribonucleoprotein. On the ER membrane, there is a channel that's plugged. Does that look like a plugged channel? You see that this little ball thing can hinge out and come this way and it can come back that way. Okay, so this is a little ball covering up the entry. Okay. This is called the translocon. I think it's called Sept 61 if you were a yeast person. Okay, it was first identified in yeast and it was called Sept 61. I think Sept stands for secretory protein. Okay, we'll call it the translocon. Okay, somewhere close to the translocon. Is a protein complex called the SRP receptor. Okay, so the beta subunit of the receptor is a transmembrane protein to anchor that receptor into the membrane, and the alpha subunit would be a peripheral membrane protein that's associated with the beta subunit. This is that alpha is the docking site for the SRP, so we're going to have to draw that in. The beta subunit is also a GTP base. Okay, so it's probably bound at any one given moment to a GTP, although apparently it doesn't bind that tightly. Okay, so I got two GTPases, the SRP and the SRP receptor. The SRP is a GTPase, the SRP is a receptor. This is way different from the kinds of G protein we're going to see. So here's the interaction. Binding to the emerging signal sequence on the ribosome. Okay. So the SRP binds to the SRP receptor. And that's actually an important contact. Let me show you what else can happen. Because SRP can bind to the A site of a ribosome, you can't bind to an empty ribosome. Okay, so draw this. This should be in a corner. This is not part of the. This is could also happen. So it's not a main part of the pathway. And it could deliver an empty ribosome to the ER. Okay? However, this is not likely. Okay, it's possible, but not likely. And here's the reason why. The SRP has a very low affinity for the SRP receptor when it doesn't carry a signal sequence. And the paper I was reading this morning called the signal sequence cargo, which actually makes sense. This binding site is 100 times greater when there's a signal sequence. Is bound to SRP. Okay, so there is a selection. There's a selection that takes place. The other selection is, the other kind of selective thing is that when this contact is made, the GTP is higher. Okay. So when the contact is made between SRP and the SRP receptor, that stimulates GTP hydrolysis, and this sequence and this thing falls apart. And I'm not going to drop it. Okay. So if that contact happens to persist long enough, GTP will be hydrolyzed, the ribosome falls off the ER, and really, except for the loss of GTP, a couple of GTPs, nothing really of consequence happened. When this contact is made, okay, and there's cargo, there's signal sequence, okay, this delays the hydrolysis of GTP. The importance of that is like, so what? That does not sound helpful. Okay. But the importance of that is it allows this contact to stabilize. So this sits down long enough because we've got a more important job to do with this contact. The energy released by these GTP hydrolyses, the two of them, is going to transfer the signal sequence from the SRP into the translocon. Okay, so we're going to see this thing get transferred, okay, to the translocon, and that's what the GTP, that's what the energy is going to be used for. This channel and right now the ball is still plugging up the hole. Okay? The SRP can go pick up another signal sequence, go bind to another ribosome, revealing a signal sequence. And the SRP is going to, will change its GDP into a GTP. And you can start the process over. So an SRP, one of these guys, can be used over and over and over and over again. And say this SRP receptor can be used over and over and over again. Okay, how does that look so far? Any questions so far? We got just a little bit more detail left. We gotta get rid of the signal the signal sequence. It's still there. We gotta get rid of it. Something funky. I'm going to push the door open, because eventually the emerging protein is going to push this door open. But here's what's going to happen that seems kind of weird. So the P site channel is continuous with the translocon channel. Okay, isn't that weird? So the signal sequence kind of flips in the translocon channel so that the N-terminus is up here. How that happens, I don't know. And I think that's a positively charged amino acid has something to do with it because of some negative charges here. And we'll look at how would that matter? Okay, so there's a little flip-flop there. So the signal sequence remains in the translocon, okay? And as each new amino acid is added, this loop gets bigger and bigger and bigger and bigger. Okay, does that can you picture that happening? So all of up here, the amino acids are being added, and that's just making this chain longer and longer, so this loop here is growing and getting larger and larger. Okay? But the signal peptidase is looming here around the translocon, along with everything else. You think that translocon is a crowded thing. And as soon as the cleavage site emerges, okay, the signal peptidase reads that signal site, or cleavage site, because it's an amino acid sequence. Okay, and it will clip the protein here. Okay, so the final, I'm not going to overdo my break. Abbreviate the picture. I'm gonna take the ball off. The growing protein actually pushes the ball open, the door open. Okay, so the signal sequence is here. Okay, then the growing protein is now here with the new N-terminus, okay, because here's the part that first 20 or so amino acids got cut off, right there, creating a C-terminus on the signal peptide and an N-terminus on the growing protein. Making the protein. Okay, yeah, Carly.
Okay, so is I might have missed it, but is the signal peptidase always on the membrane, or is it just when it opens the translocon that it comes to?
Oh, it's not opening the, no, it's always here.
Okay,
So what I have a hard time picturing until I remind myself, come on, these are just cartoons, this is not what it really looks like, is there's 360 degrees of translocon.
okay.
So there could be the signal recognition particle here, it could be anywhere. But I draw it flat, but I have to keep reminding myself that that translocon is 360 degrees, and there's proteins all over it. Okay. So yeah, I would imagine that the signal peptidase is never too far away from the signal, from the translocon, because that's where it does its job. Okay, so do you understand how it is that the signal peptide is gone way before the protein gets finished? Okay, and tomorrow we'll take a look at just how do you get this thing out of here? And I'm not exactly sure. I don't know if it slides out, but I'll show you what probably could happen to the signal, that signal peptide. But it will get degraded, and amino acids can be recycled. So all this N-terminal signal sequence is doing is allowing the protein to be made on the ribomes, on a membrane-bound ribosome. And once the docking has taken place, you don't need the signal sequence anymore. Okay, so you know, coming back to this, oh, Erin, this is yours. So you know, coming back to this, what is the thing that deviates the protein from, or gets the protein to the membrane, and not the cytoplasm. So right now, you could add N-terminal signal sequence is the thing that's going to direct the ribosome membrane. Here. And tomorrow, I have to go re-look at this. I got to re-look at this every year. We're going to look at, so how does that protein that's made on the ER become a transmembrane protein, not a luminal protein? So we'll look at the thing that, we're going to look at how we reflect the protein off the bulk flow pathway by getting